Welcome back. And today we will be starting lecture 7. So let me tell you several things we will talk about today. Today we will start the topic on ideal gas, and then the next one as well, and then the following chapter as well on what's called the kinetic theory. All right. So what is these two? These are the two main things we'll cover today. Very roughly speaking, this is a macro view of how gases react to heat. Okay, so we basically roughly talked about the effects of heat on solids and liquid. In the particular, we spend most time on looking at how they expand, and also just a tiny bit, which I refer you back to the reading, is how when adding heat to things, temperature will increase. I'll make a few extra comments today on that as well. And kinetic theory is the microscopic view of that. So now we turn to how heat affects gas. Turns out gas, it behaves drastically different from solid and liquid, right? So it's slightly interesting, the grouping. When we are interested in thermophysics, turns out gas is the odd man out. It behaves quite differently from solid and liquid. Whereas when we're studying fluids, the term fluid is basically the combination, the umbrella term for both liquid and gas, right? So in terms of motion, so in terms of the subject of kinematics, like motion, kinematics is kin is the root for motion, matics is the study of, right, like mathematics. So the study of motion, fluids, so gas and liquids behave very similarly because they don't take any definite form, right? So they're free to mostly fill the container where they live in. So they flow pretty flexibly, and we realize it's not easy to look at just the energy of it or just the mass of it. What is better is look at mass per unit volume. So that's why the first thing we introduced is a new concept called density, and we look at how we study the density of it, and instead of looking at energy, so density is mass per unit volume, right? And instead of looking at the energy of the fluid, we look at energy density, right? We take energy divided by volume. So both of the concepts, instead of looking at mass and energy, we look at mass per unit volume and energy per unit volume because the volume changes. So you divide away from the volume that you're interested in. Now you're looking at just the local intrinsic property or the fundamental intrinsic property of that substance that you're looking at. So that's what's useful for fluids, right? All right, so now we go to thermophysics, and the grouping is a little bit different. They behave slightly differently. So this lecture is focused on the gas, okay? All right, so let's put ourselves in the context of where we're leading at. So what have we learned so far? So in bullet point form, the first thing we learned is heat is an energy, not a fluid, as a lot of people thought. A lot of people think we all have experienced hot heat flow from hot to cold objects. So it's very natural. People thought, well, it's like fluids flowing from high potential to low potential, from a high height to a low height. However, it was proved by Jules, our friend, that it is not true. In fact, just another fine print is energy transfer. The symbol we use for it, right, is delta Q, or a lot of times if you've read the book, it just writes Q, but today you'll see some extra benefits of writing delta Q, and tomorrow you'll see even more benefits of emphasizing it's the transfer, it's a difference of it. So one of the sub-points we learned is that objects have internal energy. Okay. And the symbol we use for that, sometimes we'll just write E int, right? The unit is joules. So they have internal energy. Basically, it's from the internal particles moving around, and that contributes to it. Remember in 3A, we never talk about internal energy. It's always external. It's an object moving. But now we zoom in and look at, actually, even if it's not moving and not under external influence from other sources like gravity or other magnets or electric sources, itself has energy. And that is manifested in its temperature, right? If it's hot, it has actually more energy. So two things standing completely still at the same height can have different energy, and that's manifested in the temperature. So how do we quantify the internal energy? Well, if you have a device, stick a needle into the object and measure. Think about how would you measure energy? If I have a block of wood, it's at room temperature, and I ask you how many joules does it have? How would you do that? Can you take it? Is there a device in your back drawer that you can take and then stick a needle into the wood, and it'll read out, oh, it has how many joules? that's not how it works, right? The closest thing we have is a thermometer that we can stick into it, and then it will tell us how many degrees. So in everyday life, in everyday life, we measure the internal energy content with temperature. Symbol we use is T, right? The SI unit is K for Kelvin. So now it will lead me to one of the focus that I will bring up today is I will emphasize the difference between macroscopic variables and microscopic variables. Okay. So the internal energy is usually the energy for, there's several things we might be interested in. Sometimes we're interested in the total internal energy of the system. So this is about the system. Sometimes we're interested in the individual internal energy, right, of the particles in the system. So normally the relationship is the total energy is just n, how many particles you have times the individual internal energy of each particle, right? Very simple. But so these are, yeah, so individual, for example, the individual energy is each particle can has potential energy and kinetic energy. And as we'll talk about today, we'll basically focus on kinetic energy. That's why I almost forgot to mention about potential energy, because most of the time, and as we will talk about very shortly, is we focus on the kinetic energy part. So I probably shouldn't cross that out, it exists, but we're just focusing on the kinetic energy, which, as you know, is half mv squared, right? So when we're talking about individual particle, let me put an I over here, is the VI, the V. So I can be particle number 1, number 2, all the way to number n, right? It's the individual velocity will contribute to the kinetic energy, and that contributes to the internal energy of that particle, and then it contributes to the internal energy of that system. So these are microscopic variables. Macroscopic variables is you don't care about the individual particle. You just when you stick a thermometer in something, it just tells you what the system. You assign a number to the system. And now when I say the piece of wood is 20 degrees, I have no knowledge of what the individual particles is, but our lives is actually better off just knowing that number, because we can do stuff with that. We can, if it's a hot piece of iron, or if it's a ice, and I know that now, oh, the ice is -1 degree Celsius. I know that if I drop this piece of ice in a glass of water, how long it'll take to cool down some hot beverages, right? So we can actually utilize these macroscopic. We don't actually need a lot of time to know the individual behavior of things. All right, so that's the basic property. And then we mentioned there is ways that heat can transfer, right? So heat can transfer by conduction, convection, and radiation. Again, this is done. I'm not going to write everything too closely, but I want to just build onto that knowledge. Now let's zoom in and understand it a little bit better. So let's say one side is hot, one side is cold. What is really translated, as we talked about heat, is energy, and more specifically kinetic energy is one side the particles are moving, vibrating, or whatever, moving. It can be rotating, right? There's the 3 types. It can be moving linearly, translational, or rotating, or vibrating, more rapidly, and the other side is vibrating or moving much slowly, right? So this side is hot, this side is cold. How do second law tells us that the heat will always get transferred, internal energy will always get transferred via heat from hot to cold. How does that happen? It's not something a fluid move from hot to cold, but rather it's just this guy is moving so much that it's going to affect the next guy to move quite a lot, right? Let's say this is a very lazy particle, it's just standing there, much like we are today in this early morning, not moving a lot and at very low energy state. But when the other side has very high energy state, hopefully what I'm trying to provide is to jiggle the next guy enough to sort of motivate it to move more. And as this guy move more, it will motivate the other guy move more, right? On the other hand, the other guy will also drag down these guys to be a little bit slower. And after a while, everything will be in equilibrium where everything will move at the same speed, right? So after a while, this will happen. So that's how conduction works, right? And convection works with a different principle. It's when this guy moves fast, this guy moves slow, right? And what happens is this particle actually gets moved over to this side. Let's say I have 2 fast moving particles and 2 slow moving particles, right? And just by them moving around, they will redistribute themselves so that there is a fast moving particle here and a slow moving particle here. There's a fast moving and a slow moving particle here. So on average, they don't affect each other. They just moved around and now equilibrated, become equilibrium. So that's how convection works. Usually fluid is the best example. Gas is also true. If you turn on the AC on one end, the quickest way that the room becomes colder. We're in the summer right now, right? When you turn on the AC, which is at the corner of one of your in your room, when you turn that on, what is the quickest way? Do you think it makes the room cool down? Is it conduction? No, conduction will take forever. It's actually convection. It blows the air around, and then now it mixes everything together. On the other hand, for some of you who lives in northern states or in higher altitude, in the winter, when you're cold, you turn on the radiator. You turn on the, which way do you think will warm up the room the quickest? Not one of those wind blowing ones. Those would probably be convection, but just a heater, you know, a good old fashioned heater. Which way? Or actually a fireplace. This is such a foreign concept to Californians, but that which is the way? It's actually the third way, radiation. Okay, so how that works is this is a magical way where the object does not even have to be in contact. And what happens is this side there's a fast moving particle, right? And this side there's a slow moving particle. One side is hot, one side is cold. How does that work? This only works if the particles are charged. Okay, so if the moving particle is, let's say I have a box of pure neutrons. It's hard to make, but in a lab, let's say you made a box of pure neutrons. Radiation does not work that way, okay? You cannot create. The only way if you want to make a box of hot neutron to become equilibrium with a cold neutron, you have to put them together, allow them to mix by convection or conduction to slowly influence one and another to do that. Radiation only works with charged particles. But fortunately, most of the time, things are made of atoms. And what's moving around in anything that is moving will, any charged objects that's moving will emit electromagnetic waves, okay? So in an atom, what is moving the most? The electron is vigorously moving around, whereas the nucleus, the protons inside, are relatively stationary, right? So the electrons are moving more rigorously, and so overall, the charged particles are moving, there's an overall net charge that is moving quite vigorously, and that will emit EM waves in all directions, right? So moving charges will imply EM wave, electromagnetic waves. Electromagnetic waves is a huge spectrum from visible light to infrared to X-rays to radio waves, as you know. And the spectrum that we can see is visible light. The spectrum that we can feel is infrared. And that's why there's infrared detectors of taking a temperature when you go through a clinic, right? Because we are warm bodies that emit, we have made of atoms, they actually move around and they emit electromagnetic waves, right? And what these devices pick up is they pick up infrared frequency, and they will detect this radiation. So some of these go over here, and just like moving charge will make EM waves will also make charges move. Okay, it's the same process. Okay, so this EM wave will make these move faster that way. Okay, so that's how radiation works. Notice radiation is actually going one direction, and it doesn't need a medium in between. And thank God for that, because we feel warm in the summer on Earth because of the sun can radiate energy to us, radiate infrared energy. In fact, the sun radiates, also when something radiates, it doesn't discriminate. It's very democratic. It radiates in all spectrum, all frequencies. So what we see from sunlight is the visible part of that EM wave that is coming to us from the sun. What we feel when we stick our hands outside on a hot day, we feel that radiation. What we feel is the infrared spectrum. It's because our molecules, our hands, our skin is actually, it has a resonant frequency. This is not part of the topic, but if you know roughly what resonant frequency is, our human skin molecules has a natural frequency that is actually in resonance with the infrared frequency. So if there is radio waves coming through, it doesn't really bother us because it just passed right through. It doesn't really resonate. It might affect a molecule or two in our hands, but mostly just go straight through. But if it's infrared that comes in, it jiggles our molecules so much that when there's motion, there's friction, and we feel that as heat. Okay, so when next time you touch your hand on a stove, don't do that. But if you do, what happens is the stove, that's by conduction, it jiggles your molecules so much. That's not by radiation. But if you don't touch the stove, you just hover above it, then what you feel from that heat is that radiation, the infrared radiation jiggling your molecules. All right, you can read more about that in 19.10. Notice this, actually the textbook went in a little bit more depth. Let me put a star there so that just look at the syllabus and say limited examinability. We're not gonna, it's a little bit beyond the course to study all the formulas for each of these processes. But so when you read through it, I still encourage you to read through it and get the qualitative sense out of it to understand. I think that would be the interesting part, but if you get confused with the formulas, you feel free to skip that. We will not be tested on that. All right, so now that we have this, we know that how, so now we know how if one object is hot and you can actually take some heat and put it to the other side by one of these three methods, what will happen now? What happens? So now that I've, let's say A is the stove and B is a cup of water on top of the stove. So now it's full conduction, conducting heat into the glass of water, or you put a piece of metal on top, what will happen to this? So now let's zoom into B and focus on that. Well, first of all, answer number one, internal energy of B will increase, right? The internal energy of the object of interest will increase. And as we mentioned, this is measured by, we can't measure the microscopic energy easily, but we can measure the macroscopic variable T easily with a thermometer. So T will increase, right? So this is for all objects. All matter, this would happen, okay? But now for only solids and liquids, for solid and liquid, what usually happens is the pressure is fixed. Usually at ATM, atmospheric pressure. If I warm up a cup of water in your kitchen, if you go to your pantry and then warm up a cup of water, it's still in contact with the air, right? Because we are under atmospheric pressure, as we learned from last week, constantly, and that is a very dominant effect, and it'll basically maintain a constant pressure for it. Even if the liquid suddenly have more pressure from that temperature, it will very quickly become equilibrium with the surrounding, and so the pressure is kind of hold fixed for most of the time when you heat up liquids or solid. Okay? That is not true for gas, which we'll see. So as a result, since the pressure is fixed, how will it react? It will usually react by the volume increasing. Let me make this delta to emphasize this change, right? So the volume will increase. So that's the only way it usually reacts. And how much now, you ask? Because if you don't study a course, or you don't study a physics course take a proper physics course like this, and if you're just trying to learn random facts, watch a documentary, they'll tell you, okay, that's the end of it. But since we're doing an actual course, we want to do one step further. We need to know the technical side, and not only what will it happen, but how much it will happen, right? That's the calculation part of the course to develop that skill. So how much we have basically discussed, it's quantified by this coefficient alpha, right? Alpha V, let's say. And it depends on the original volume, and it depends on how much the temperature change. So one more time, the logic is here. You transfer heat from A to B. B's internal energy will increase. B's temperature will increase. The pressure is fixed, which means if it increases, the volume, this is how it will react, okay? And by how much? It's each material has a different value. You look up the table or called beta in your textbook, and it depends on how big it originally is. The bigger it is, it will expand more, right? By the same amount of heat you add to it, and how much how much temperature you heat it up by. And now, so maybe I should say, how do you know how much temperature? Well, it's given by what you have read on your own, right? So you supply some heat. And the heat will, this is actually a good sequence to remember. You supply heat, it will increase the temperature, and then the temperature will increase the volume. So this is how the heat transfer cycle works. 1, 2, 3, like that. Okay. A caveat here, just to re-emphasize this, this formula works only at constant pressure. This formula works only at constant pressure. As a result, one of the biggest mistakes I see in people when in the past in this course is people applying either of these formulas to gas. Because as I will tell you right now, pressure is not fixed for gas. So so make a note in your own notes that never apply these two formulas to gas. They don't work. With a slight modification, this one does, but not the way you learned it right now, okay? So this we don't write this at constant pressure symbol a lot of the times, but because it's treated as understood. But a lot of people don't understand that. And hopefully now that I've emphasized it, you do. All right, so now the question is, if T is not fixed, then what happens? Well, actually, so both, for gas, both P and V can both increase. Now we want to know how much, and that's what we will talk about. Okay, does that make sense? Okay, so this is so this leads to our new chapter. So yesterday I was pondering, should I split the chapter 4 into 2? But sorry, so I go back on it. I'm going. So I won't split it into. It probably doesn't matter too much to you when you're listening on this. It's just for my admin sorting purpose. So I forget about the chapter 6 that I wrote from yesterday's notes. Just group that into the previous chapters according to the syllabus. Just refer to that. So I will revert to the original way. Okay, so we are talking about ideal gas. The chapter number only affects you when you're studying for the final exam to look at the sequence of things. In fact, we're focusing on the macroscopic behavior of ideal gas. Okay, so you can, the reference chapter for here for your post-lecture reading is 17.629. Quick comment on post-lecture reading. As you know, that is an expected component of the course, although it's not, I'm not going to be your dad and monitor you to do that. That's the independent part, but that is part of a component. And a lot of lecturers assign pre-lecture reading, as some of you have probably experienced in different courses for pre-lecture reading. I think that is definitely a good idea if you have the self-discipline to do pre-lecture reading to get an idea before you come to a lecture. But that is a little bit different because they do a very popular way to do lectures is in lecture, you just go through all the informative stuff, all the actual information, which, let's face it, can be quite dry. You remember this, you need to know this, you need to know this. And that's why to do that, you very easily get lost in that sequence of the forest of dry details. So if you do a pre-lecture reading, then you have a big picture and you go in and that's it. So I do a different type of lecturing style, which I like a little bit more, is by the way, I still encourage pre-lecture reading if you do, and for those who really want to, get an A and strive for the best, the more times you get exposed to the topic, the better, really. So yeah, but personally, I always have the problem of self-motivation and be able to, sit down and read through the textbook is already that dry information and to absorb that. So I rather use the lecture to provide the motivations. In fact, let me give you a study tip, and so you get a better idea of what the lectures are for, and not rely this on as an exam resource. The textbook is, that's where you need to learn your stuff, is I use this as the motivation of the subject. So I will share, so my lectures, the purpose is to supply motivation and sometimes supply the history of things and supply the context of things. The goal is to make your reading easier from there on, right? So I won't make pre-lecture reading a requirement, but in some sense, I'm making post-lecture reading a requirement. And I think that it's much more enjoyable to look at the technical stuff once you have the idea. Okay, so your side is so you learn. So I do that in lecture. You do this at home, the technical details and the problem solving skills. This one from reading, this one from homework. Okay. Back to the topic. Okay, so what is ideal gas? What are we interested in? So my subtitle, I would call this, it's the theory of heat. Actually, no, sorry. So this is actually quite interesting. It's the whole macroscopic behavior of ideal gas. Physicists have sorted this out. A little bit of history, as we were saying. Physicists sorted this out before even the invention or the discovery that atoms exist. It's quite impressive that they can build machines, steam engines and stuff. They know they can manipulate heat in a very beneficial and advantageous way without even knowing what heat is made out of or what substance is made out of. The definitive proof that atoms exist is actually Einstein, who wrote a paper on Brownian motion, one of his famous papers in 1905. this brilliant guy, in 1905, he published 5 papers, and each of those 5 papers is revolutionary. Not sometimes physicists, scientists, you publish one paper that is revolutionary, that is already a great achievement in your lifetime. If in one year you publish 5 papers, those include one paper on Brownian motion, one paper basically kickstarted quantum mechanics, one paper about relativity, one paper about E equals mc squared. So each of these are revolutionary to physics, which is amazing. The Brownian motion is in 1905, and all these theories that we're studying is from the 17th to 18th century. So almost like a century before, probably 18th century is more realistic, a century before the atoms are definitively proved. Right, so just to put that, to give you an idea. And so therefore, in this chapter, we're going to focus on macroscopic variables. Okay. And then next chapter, so chapter 7, we'll focus on the microscopic variables of ideal gas, okay? So here, as you already can tell, these are our primary macroscopic variables, P, V, and T, right? And now, both P and V was introduced before. So P was earlier in this course, V is the volume, you know that from 3A. Temperature is the new thing that we are addressing here, okay? And in the microscopic variables, the variables would be VI, the individual particle's velocity, or the individual particle's kinetic energy, or the total or the system's kinetic energy. Right? These are microscopic variables that we'll focus on in the next chapter. All right, now that leads us into immediately one opening question is how, remember that temperature, how did we define temperature? Because now we're focusing on temperature. So in the first chapter, we actually gave the modern definition of temperature, which is a measurement of average kinetic energy. So what is average kinetic energy? So you're looking at the kinetic energy of an individual particle, but you look at the average. Sometimes we put a bar above a variable. This denotes average in math. It's a measure of average kinetic energy of individual particles. This is the definition of temperature. But if this whole theory is sorted out before the existence, knowing that stuff was made out of atoms and individual particles, how do people define temperature? So we actually need a little bit old school definition of temperature. So there's actually 2. There's a modern definition, which is the one we presented right off the bat. But here, yeah, so that's one question that we will answer, okay? And another question that we'll answer is, so question 1, question 2, how do PV and T related? How are PV and T related? How do they interrelate to each other? How do they affect each other? Okay. So as usual, let's start with the definition, and let's define what do we mean by ideal gas. Okay, so this is going to be interesting as soon as you see the definition, because it sounds dumb. An ideal gas is a gas that obeys the ideal gas law. Okay. In fact, it sounds very circular, right? It sounds, you might ask, well, what's the ideal gas law? It's a law that ideal gas obeys, but it's actually not that circular. So let me explain the definition. So the ideal gas law, again, you will, I'll defer it to you to do a little bit of reading on that, and a lot of you probably have some basic idea of the ideal gas law already. So PV equals nRT, and hope you have also seen the other version to write as NKT. So we'll talk more about that in a second. In physics, we're usually interested in the latter, in the NKT version, but we also use the nRT. There's different times, each is more useful. This is actually more fundamental, so, but everyday life, this is more useful. That's why probably in everyday chemistry, this is more used, but this is more the fundamental principle. We'll see what that difference is. But so what this tells me is if I have a box of gas, right, and if I increase the temperature of this and keep the volume constant, as you can see, if I keep the volume constant, this is constant, then pressure is proportional, because let's say the number of molecules is the same, this is a constant, and if I increase the temperature, the pressure will increase, right? So this is proportional, okay? And if this time, I allow the volume to vary, okay? So I actually allow the volume, so this is the gas, I increase the temperature, so it's going to expand from here to here. I allow this box to freely, there's a valve in between that can expand. What is the relationship? The volume is actually proportion to the temperature, right? And finally, if I keep the temperature constant, if I fix the temperature and I allow the volume to change, let's say this time I do the opposite, I push the valve back in and squeeze the gas, what will happen to the pressure? I compress it, right? Well, the pressure will increase. And how does it increase? It follows this relationship. So if I want to know if what I have in this box is an ideal gas or not, I need to check these three things. If it satisfies all these three relationships, then it is an ideal gas. Okay. So all these three, of course, combine into this one law. As you can see, I just made these three out of it, right? You can stitch them back together. So that's the ideal gas law. So when we say something is an ideal gas, so this is actually not a circular definition. When I say something is an ideal gas, we're saying it satisfies these three properties, or more succinctly, it satisfies this property. Okay, right? Hopefully that clears it up. All right, let's look at the key properties of this ideal gas that we just learned. Okay, so all right, I should stop using abbreviations. Ideal gas. Okay. There's three key properties, okay? So first, there is no intermolecular force. When I say no, I mean negligible, right? If I mean actually ideal, then there is no intermolecular force. And the next thing is, all the internal energy is kinetic. Okay, so now you know why I almost forgot to mention potential, because when we focus on ideal gas, there's no potential energy. No internal potential energy. And finally, all collisions are elastic. So if you forget what does that mean, in 3A, that means when two things collide, the kinetic energy is conserved. Now, total energy is always conserved, but sometimes when you collide, some of the energy gets transformed into sound and heat, right? So if two hands collide like this, part of it translates into sound energy and heat energy. So that's not an elastic collision because the kinetic energy is not conserved. But if all the kinetic energy is conserved, there's nothing get lost in the kinetic energy doesn't get transformed into sound energy or some potential energy or whatever, then it's elastic. So as you can see, these two things are actually the same statement. When we say all energy is purely kinetic, there is never any potential energy or other types of energy in the ideal gas. It's all purely kinetic. In fact, you see all three is actually equivalent because each force in physics associates with an energy. So intermolecular force is actually the residue electrostatic force, as we talked about in yesterday's lecture. It's a residue electrostatic potential, electrostatic force, which means there's an electrostatic potential energy, or electric potential energy for short, which we'll cover in the next week about electric potential energies, and you'll get an idea of these intermolecular forces. So when I say everything is kinetic, that means there's no intermolecular force. So you see all these three statements are basically it's the same way of saying the same things, but give you a better visual. Now, actually, we can derive all these from the ideal gas law as well. These are direct consequence from PV equals to nRT, but that's a little bit more subtle, and we won't actually do the proof. Okay. So when is it a good approximation? When is a gas ideal? There's two scenarios, either when it's very high temperature or very low pressure. Okay. Low pressure or low density. Okay. So when it's high temperature, you can tell because temperature is a measurement of individual particles, average kinetic energy. So that means the kinetic energy dominates. So even though ideal gas does not exist in real world, when you have high temperature, it's pretty good approximation. Or you can achieve it by making it a low density or low pressure, because now they are very far apart, right? If there's low density. And as a result, if there is any intermolecular forces, is negligible, is at least subdominant / negligible. Okay. So when realistic, okay, that's all good. What do I mean by high? What do I mean by low pressure? What do I mean by high temperature? All right, turns out it doesn't have to be that high. When we're talking, if you go down to almost absolute zero, yeah, sure, you can't have, the gas will no longer be ideal if you cool it down to that much. But actually room temperature gas is actually very much close to an ideal gas. So if you use the ideal gas formulas to calculate stuff in room temperature, the accuracy is incredible. Maybe there's a discrepancy at the 4th or 5 decimal place, but let me give you a ruler. Can you measure things to 5 decimal place? No, I doubt it. You can probably only measure things to 1 decimal place, one or two significant figures, right? That's, or if you have more precise device, yes, maybe you can. But realistically, if you are, so it's actually a very good approximation unless you care about that 5th decimal place. These formulas are much simpler to handle than real gases, all right? Let's introduce, this is a standard thing. Sometimes when we don't talk about what temperature or pressure we're working with, we assume this idea of STP. You might have heard of that in chemistry. It means standard temperature and pressure. Standard temperature and pressure, you can Google that a little bit more. I'm not going to talk about that too much. The standard, it's 0 degrees Celsius and 1 atmospheric pressure. Very, very simple. Now, when you're doing physics, be careful. Don't use these units. Right? Make sure you use SI units. SI base units is 273 Kelvin and 101 kPa. So this, when you're at this is called standard temperature and pressure. And actually most gas, even at 0 degrees, at freezing temperature, the gas is pretty ideal, okay? I've got a question on the chat asking, is chapter 19 a self-reading exercise? No, 19 is not, okay? You can go back to my lecture notes. I have quoted which one is, or 19.10 maybe you're referring to, 19.10. Now, okay, so let me briefly mention the historic origin of the ideal gas law. And so it actually didn't came from one person from the get-go. It actually came from 3 different laws, 3 different investigations. There's Boyle's law, and then there's Charles' law, and then there is pressure law. I guess there's no name. People forgot who made it or whatever. So Boyle's discovered that pressure is inversely proportional to volume as long as you keep the temperature constant. So when you compress the gas, as I draw, okay, I'm not going to redraw that. You can look at over here. Right? So if you keep the temperature constant, pressure is, you change the pressure, the volume changes inversely proportionally. And this one states that, Charles states that temperature is proportional to this. He discovered that by doing a lot of experiments and realized a lot of gas satisfies this. And then some other guy also found that if you keep the volume constant, pressure will be proportional to whatever temperature change, like that. Okay, so these 3, when you put, now that, so how you can combine them is, after that, after these 3 are discovered, now you can write down, remember proportionality means it's some constant times the other variable, right? And then you have volume is also, so as a result, this actually means PV equals to some constant, right? But then you see if you keep pressure constant, so as long as you keep pressure constant, then V is also proportional to T. So that's another, let me use different constants. Yeah, let me use K1 and K2. K1, K2, T, right? So I can, that means if I keep P constant, then this would be, right, then I can multiply P on both sides like this. But if I'm keeping P constant, this is just another constant. We can call it K3, right? So we got the result PV is equals to some constant times T. Okay. And then you can check that this is automatically satisfied as well, because if I keep V constant, right, then I automatically have the relationship that P is proportional to T. So I can combine it basically into this one law. So all of them gets combined into, let me divide the T to the other side. It is sometimes written like this. Okay, so let me summarize. This is a perfectly, sometimes if you're asked to quote the ideal gas law, let's say in a test or exam or just in the future, if you need to refer to ideal gas law, all 3 of versions is completely fine. So you can write this, you can write this, or you can write this. So all 3 are equally fine. Okay, so they're all the ideal gas law. Right? So this is particularly useful when you are doing practical things, especially when you, so when to use which, because I know one thing that is immediately in top of your head is if you have different versions of the same thing, students are immediately very confused. Okay, then what you'll be confused by the amount of choices you have. So choices is not always a good thing, right? So you need to know when to use which. So if you remember, we have dealt with this type of formulas before in fluids. Something equals constant, and now you have learned the lesson. You know when to use this is when you compare things in 2 points, right? So if you need to compare 2 points, then you use the first version. Now, also alternatively, you can compare 2 times. So you can actually have a before and after. This is actually quite more popular in thermophysics. Is before I heat it up, and then let's say I burn it, and then now I heat it up, so the temperature increase, and then now you compare. So how do you compare? You label P1 V1 T1 equals P2 V2 T2, like that, right? Just like Bernoulli's equation, just like the continuity equation, all those things. So I told you this skill will come back, right? Every now and then in physics, you will see it. Sometimes it's not just A equals B, it's A, B, C, D, E, F equals constant, right? So these types do come, and you use it this way. Let's say if you fix the volume, so V1 equals to V2, that, right? Then if V1 equals to V2, you can cancel that out, and you can do a lot of problem solving with that. Now, caveat over here, put a star over here, and remember one very important thing. These two are only true if temperature is measured in Kelvin. Okay. Why? Because they did the experiment of this. So Boyles did the experiment, and he plot a graph like this, and he plot on one side he put P, and on the other side he put V. Well, if you plot this, it doesn't really help, because if P is proportional to inverse V, you'll get something like this, because it's almost like Y equals to 1 over X kind of thing, right? P equals to constant over V, right? So you can't really tell what this curve is. But if you're a little bit smarter, you can now take your data, divide everything by 1 first, take 1 and divide it by first, and then plot this relationship. Now, if you look at the formula, it's constant times 1 over V, right? So now you actually get a straight line right through over here. And when you get I'll circle back to that in a second. But the other two is directly proportional, so this is easier to plot. So you just directly plot P against T. Now, this is actually not proportional. Draw it like this. If you plot P over T, you get something like this. Proportional means, first of all, if one is 0, the other has to be 0, right? But this doesn't happen if you measure things in Celsius. Same goes with volume. If you take the volume and temperature, if you measure it in Celsius, this is what's called a linear relationship, not a proportional relationship. It's a straight line, but doesn't start from 0. So 1 unit increase in here. So let's say if this goes from 1 to 2, this goes from 10 to maybe from 11 to 12. This one increased by 50%. So this one increased by 100%. This one increased by a small percentage. You see the percentage does not equal. Whereas if it goes through the 0, if this goes from 1 to 2, this will go from 1 to 2, or it doesn't have to be 1 to 2, but if the line is steeper, let's say it's actually steeper, this goes from 3 to 6, or something like that, right? This one is 100% increase. This is going to be 100% increase. So what you do is you cleverly extrapolate it back and redefine your temperature scale. Instead of calling this 0, because who cares about 0 degrees? Sure, it's the freezing point of water, which is useful for human beings because we live on Earth and 60% of stuff is water. So it's everywhere, so it's useful that way. But for the universe, it doesn't really care about water being anything special. It cares more about how PV and T, these variables, relate to each other. So if you extrapolate it back and actually call this 0 and redefine this as Kelvin, right? We don't want to do too much crazy math. So 1 degree change in Celsius, we'll just keep that as 1 degree change in Kelvin. So these scales actually overlap anytime after 0 degrees Celsius. So you don't have like converting miles to kilometers or inches to centimeters, where if you look at a ruler, 1 inch and 1 centimeters is not the same, right? One is more densely packed than the other. But for Kelvin, people were like, let's not make things too complicated. Let's make them equal spacing, right? The spacing between Kelvin and spacing between Celsius is different. We just make the starting point different. And if we choose the spacing that way, then we realize you need 270 more spacings before you get to the 0 degree Celsius, or equivalent in 270 minus 273 Kelvin, and we call this absolute 0. Right. Okay, and same logic. Once you define the absolute scale, people realize all these proportionality formulas hold. So let me put that in red. These only hold if T in Kelvin, right? Otherwise, they're not proportional. Otherwise, not proportional. And most dangerous of all, if they're not proportional, what law does not work anymore? The ideal gas law. So that means anytime the T you plug in here, it has to be in Kelvin. This is one of the major mistakes people make in plugging in Celsius into the ideal gas law. Disaster would happen. It will blow up. Okay. All right, good. I also talked about when can you use Celsius last time. If you know what you're doing, if you're talking about change, you can use Celsius. And the last thing I need to talk about here, lastly, is between NK versus NR. So what is this? Let's define. Remember, when I state a law, PV equals NKT, I need to define each of the variables. So this is the pressure of the system, volume of the system, T is the temperature of the system, K is the Boltzmann constant. If you use the NR version, this is called a universal gas constant. If you need to label this in exams, constant. Boltzmann constant, it's 1.23 times 10 to the power of minus 23 in SI units. I actually don't memorize all these units. So technically there's a unit there, but it's made out of joules and newtons and MKS built together. The beauty of my way of doing this problem solving stuff is I don't have to worry about the units, right? Every time I just plug in this number, okay? Now, Boltzmann constant is very obscure to remember. Is it 27 or 23 actually? Someone correct me later on, okay? I forgot. Yeah, so it's very difficult to remember, case in point. Actually, the NRT version is more friendly because I actually remember this for real, right? It's 8.31 in terms of SI units. Okay, so it's a very nice number. It's it's a digit from 0 to 10. It's more nice to use. Now, what is N, capital N and small n? Capital N is the number of particles in the system. Okay, so as we talked about, that can mean atoms or molecules, etc. In the system. Okay. So whatever the system is, right? So if you have a tank of gas that is purely, what's a element that just exists on its own? Hydrogen. So if you just have a gas of hydrogen like this, right? Well, the N refers to the number of hydrogen atoms. If you have a gas of helium or oxygen or nitrogen, right? Like all these, right? So here the N doesn't refer to how many oxygen atoms you have, but it refers to how many oxygen molecules you have. Because as far as our problem of interest is concerned, the oxygen O2 doesn't get break apart. So you don't count individual ones, but you just zoom out and assume it's one blob and follow that blob, right? And little n is the number of moles of particles. Okay. And 1 mole is, you know better than I do, is 6.02 times 10 to the 23. I think that's actually 27. I think I crossed my numbers. Yeah, but you can just Google that and double check. Okay, so probably most of you are already very comfortable with moles. If you're not, here want to give you the idea. Let's say I introduce a new variable called ND. It's the number of dozens of particle. It's the same idea, okay? So what here, 1 dozen is equals to 12. 1 mole is 6.02 times 10. I'm not hiding any SI units. There is no SI units. It's literally mole. The word mole equals to this number. I could have as well called this another number. In fact, there is a symbol for it. We could call it Avogadro's number, like you could call it NA. But treat mole like this 4-letter MOLE or MOL as one variable. Okay, just like treating this as 12. How do you use it? So let's say I have a gas like this, and let's say I have actually 120 particles. So if I actually count them, I have 120. Well, 120 is 12 times 10, or let me write it as 10 times 12. But 12 can be replaced by the word dozen. And there you have it, right? So you see, 12 is 1 dozen, right? if I want to really break this down, just for clarity. So 120 number of particles is 10 dozen. That's how you can convert from one to another. Oh, thank you. Thank you, guys. It is 23. Good. That actually makes sense. Yeah, appreciate it. And yeah, so here, what do you get? So what is ND? ND is 10. Okay. So if N is 120, then ND is 10. It's the number. It's how many dozens. Okay, it's this number over here. How many dozens? Okay. So you can convert it back. Convert the other way. How would you do it? Let's say I have 10 dozens, right? So let me break it really down. So treat that as 10 times of one dozen. So there's 10 amount of dozens, right? But a dozen is 12, so it's 120. Okay, so if you have ND, we go one way, you take 12 times ND, that will give you N. Okay? Similarly, if you have N as the as moles, then what you do is you take, so 12 is that important number, right? In fact, let me write this the other way around. Times 12, because this represents dozen. You take N and multiply by that Avogadro's number, right? Or 6.02 times 10 to 23, and that will give you capital N. Okay. Which value is bigger? Is usually this number bigger or this number bigger? Well, this times this gives you this. So this is huge. That's why we use capital N for it, right? Yeah, so sometimes this is a nice sanity check. If you do your homework problems or exam and you suddenly get a huge number, then or so suddenly you realize this number is larger than this, you've made mixed up and used divide instead of times, and put it on the wrong side. So yeah, as long as you're defining variables, either way is fine. Now, practically, which one do you use? Depends on the problem. If it tells you you're given how many moles, don't be stupid. Just use the mole version. If they tell you how many particles is in the gas content, then again, you're making your life difficult if you use the moles version and just use the other one. Here's a nice check at home for you. So check that. NR equals to NK. This is actually identical to, I'm going to emphasize it with the 3-stroke equal signs, okay? Yeah. So find this value, plug in, let's say 1 mole, ask yourself, so Google this, which I actually wrote down already. Here's your task, find out how many N is 1 mole, and then check if this is equal, okay? It should be. So that's the end here, this chapter. Right, so now this is the theory. Of course, I gave you the background, the theory, the motivation, and a little bit of extra tips on problem solving. You can read, I encourage you to go and read all the examples in the textbook. And there's those exercise ABCDs. Those are a good way to test your understanding, okay? That's probably the first thing I would do. Okay, so now let's use the rest of the time to discuss the kinetic theory, what's called the so-called kinetic theory of ideal gas. And as we mentioned, this is the microscopic side of things. And the reference chapter here is 18.1 to 2. Now, in our course, we actually won't go through too much of chapter 18 as a whole. 1 to 2 is, I think, don't quote me on this, look at the syllabus for sure, but 1 to 2 is the main part on it. So this is a very short chapter as far as we're concerned. Even if you look at the textbook, you see the rest of the sub-chapters, most of them have a star on it, which is a little bit of extra optional chapters. Okay, so yeah, so this is relatively short, and there's only a couple of takeaways, okay? So, let's see. Let me write down the opening question first. So here's the question we want to address in this chapter, all right? Is we've talked about the macroscopic variables, which is P, V, and T, and we know the microscopic variable, which is the individual's velocity of the particle, which means the individual kinetic energy of the particle. Now, can we get one from another, right? Can we measure, if I know every single velocity, can I find out what the pressure is? And vice versa, right? Now I want to draw a bridge between these two and tie the whole subject together. The kinetic theory of ideal gas was developed way later by Lord Kelvin and a lot of other 19th century physicists, almost again 100 years after the macroscopic theory was developed by Joules and to some degree Laplace, Newton, all those all those guys we've heard of before. This developed the chapter 6 theory, right? The ideal gas law, Boyle's, those people were responsible. Planck, Clausius, Kelvin, the guy who invented the Kelvin scale, right? Worked a lot on realize this. And that's when they only were able to do this once they realized and matter is made out of atoms, made out of stuff like that. So this was after they know atoms exist. Okay. From our everyday knowledge to the macroscopic variables. Now, as I mentioned, the most important one is temperature, because that's the new variable we're talking about here. How do we measure temperature? Well, temperature before we defined it as the average kinetic energy. So this symbol, average kinetic energy of individual, is a measurement of, it's a measurement of, as we'll see, it's not exactly, but it's roughly the average energy of individual particles. This is the microscopic. Every term over here, I'm using microscopic variables. So how do we do this? Well, actually, the temperature is basically defined via ideal gas law. You rearrange it like this. Okay. So in practice, what do? Normally, so you keep the number constant. Well, the Boltzmann constant is always a constant. So you keep the number of particles fixed inside a box, right? And then now you try to change its pressure by changing its volume. So you change its volume, you change its pressure like that, and then you plot a graph. You know that they're proportional. Let's say it's a very steep graph like this. Let's say a PV graph. And this goes from 1 to, you increase the volume from 1 to 2, and this goes from 3 to 6 like that. Now you have the slope, right? So you measure the slope of this because if I rewrite this, that's the macroscopic definition. But if you rewrite this, you can rewrite it as some constant times, or sorry, I should say, I can write P is equals to 1 over NKT divided by V, like this first, right? So this looks like Y equals to mx plus C kind of formula with no plus C, first of all. So this is usually the slope, right? So if I have P playing the role of Y and 1 over V, sorry, I need to plot 1 over V, 1 over V, this is the slope. So if I take the slope of this, right, and then I divide, so the slope M, and I take that value, I take it and divide by NK, I will get the temperatures. That's how you can tell the temperature without knowing individual particles, just from macroscopic variables of P and V, like that. Okay. So the question is, how do I link these two together? So there is 4 basic assumptions before we can prove that. And this is listed in your book, so I will save a little time and not cover that. So in the textbook, 18.1. But just be aware there's 4 assumptions before we do that. Let's see. I'm just debating, should I tell you the conclusion first or show you the logic of it? And usually I like the former. I usually like to show you the conclusion first, as you've probably seen my style. But this conclusion won't really make much sense. So let's build this up. All right, so let's have, if you have a box of gas like this, let's see, so remember our goal is to relate. So the goal is to relate VI, KEI, and ask, if I know this, can I predict PVT? Or the other way around, if I know this, can I predict the individual particles? Okay. Now, obviously, if you know the microscopic variables, yes, you can probably hope that there's a way, if I have a nice formula, I can take this and then calculate the macroscopic one. The other way, even before doing any math, you know that that's impossible. All right. If I tell you, because the macroscopic, it's only about averages. So if I tell you what is the mass of every single American in the country, you can easily calculate the average weight of an American in the country. But if I tell you the average weight, there's no way you can know how individual person's weight is. So the best you can do is if I tell you something like that, a macroscopic variable, like how much the average weight of people are in the country. The best you can do is you can calculate something average about the microscopic. Like, for example, you want to know how many calories people eat per day. That you can't tell, do you eat more or less, but if I tell you how much do an average person weigh, you can maybe in some hope to calculate how much do an average person eat, right? But not individual, okay? So the best we can do when we go backwards is know the average velocity and the average kinetic energy. After a while, I'll drop that subscript and I'll just write this. But for now, I know you might not be familiar with this notation, so I'm going to write a subscript to remind you as well. And I really encourage subscripts even when you're doing exams, because that makes things clear and you have a better chance of getting partial credit for that when things are clear. Okay, it also helps your learning. That's the main goal, not getting points, but it helps because the points is designed to reflect the things that we want you to learn. Okay, so this is how we can go about it to do it. So we have a box of gas. So look, each particle, what is the microscopic variable? Each particle is moving at some velocity. So it has some x component and a y component and maybe a z component like this, right? So let me simplify the picture a little bit and what's happening. So you have a particle and it's probably moving like this. It's bouncing on the walls, bouncing, and keep moving around. Okay, so that's a little cleaner picture of what's going on. And what's happening is you can actually just look at the x direction of things. Let me just plot its Vx graph. So in fact, let me plot where it is on the x direction. So let's say this is the box of length L, right? So this is minus L over 2 like this, right? So this is the boundary of the box. I'm making L over 2 so that I can make the origin 0 like this. Doesn't matter. So originally the object, let's say it's here, and then if I follow this path that I'm tracing, then it's going first here, and then here, and then here, like this, right? So that's what's happening at a speed of Vx. Or I can plot its y direction. Right? Again, let's say this is a square box. Right? So L over 2 minus L over 2. Right? So the particle is here, and it goes up, goes down, goes up again, like this. Right? And I can trace its motion. I can do it for z as well, like that. Okay, so let's attempt to prove the ideal gas law, attempt to derive the ideal gas law from the individual particle, the microscopic individual particle motion. So on the left-hand side of this means left-hand side of the ideal gas law is PV, right? And what is P? P is the force per unit area, the perpendicular force per unit area. And what is the volume of a box? Let's keep things simple. Let's say it's just L cubed, right? It's a square box like that, okay? The area is basically L square, right? So as a result, you can cancel that out, and that's F perpendicular times L. What does that mean is, if I have this side of the area, right, and you have a particle hitting the area, it's going to provide a perpendicular force on that area. So now this guy would experience pressure, okay? But what we need to put here is we need to put the total force from all particles to get the pressure, because one particle does not give all the pressure. A lot of particles all the particles hitting the wall will give a pressure, all right? So that's the first thing. So we need to put in the all. Of course, so if you have n particles, usually just multiply that by capital N. Okay? So now you see why capital N is more favored in physics, because we are looking at how each particle moves. So what is this? Let's look at this for one particle first. For one particle on the wall. Actually, let me write due to one particle on the wall. Remember, force is always due to something on something, right? Due to one particle on the wall, and then we'll multiply that by n, okay? So let's look at the magnitude first, the magnitude of the force, because why do I care about the magnitude only? Because sometimes it hits to the right, sometimes it hits to the left, right? And I want actually all the walls, okay? So I need to look at the x direction, y direction, and z direction. But each direction is very symmetric because of the randomness of this process. So if I look at one direction, I can later on just multiply that by 3, something like that. And I look at the magnitude of the force on wall from one particle, because sometimes it moves to the right and it hits, it's positive, sometimes it's negative. I just want, okay, let me look at the force on one wall, and then I will multiply by how many times it hits the wall. It hits any wall, in fact, okay? And then I will get the total force, okay? So if you remember, force is actually, it's ma, but a better way to say that, a more sophisticated way, is dp dt. So I need a perpendicular momentum, change in momentum. So this is, if the force is constant, which it is, so if the force or pressure equals to, in equilibrium, I should say, then this will be just delta P over delta T. So you change a derivative into a easy change. So if you're scared about derivative, most of the time this gets just changed into deltas. Okay. So what does delta mean? You know very well what that means is the final momentum minus the initial momentum over delta T. Okay. So P is momentum. Don't get that wrong. This is little p, not capital P for pressure. Okay. So, sorry, momentum. Yeah. Okay. So what is delta P? So delta P, when colliding on wall, is momentum is final, is mv. So we want the final minus initial. But the mass doesn't change when it collides with the wall, right? So we just need this. So what happens when something collides to the wall, right? So at first, let's say you have Vx, and then you collide. If it's perfectly elastic, it will bounce up by minus Vx, right? So initial is final is minus Vx in the x direction. Initial is Vx, right? So together, this is minus 2 mvx. So the magnitude of this is just 2 mvx. The absolute value, right, of that is just 2 mvx. Okay? But this is one particle colliding on one wall. So how many collisions does this one particle make? It doesn't only collide on the wall once, it makes a lot of collisions, right? So within delta t, within a certain time, the question is how many collisions it makes. Well, first of all, in delta t, it moves by Vx delta t distance. So it moves this much distance, right? Because velocity is delta x delta t. So it moves this amount of distance. So it would have, so if the box is length L, so let's say, so if your box has length L, right? And it's moving within delta t, it has moved, let's say it's the box is 1 meter long, and in delta t, it can move within 1 second, it moves 10 meters. Let's say it's moving very fast at 10 meters per second, right? So how many collisions will it make? Well, it would be delta x divided by 2L, because it'll make 20 collisions, right? So it'll make 5 collisions. So in 1 second, it can move 10 meters. That means, let's see if that makes sense. You can think through that a little bit more carefully, just for time. I'll move on. This is the right value. So you take that, divide by twice its length. So if you, yeah, you can read the textbook for that a little bit more clearer. So, right, so that's how much they would have that many collisions. So the force of one particle on the wall is the number of collisions, which is this, which we can write this as Vx delta t over 2L. This is the number of collision, this much number of collisions. So Vx delta t over 2L times the force of one collision, which is 2mxv, right here, per unit time. And that gives us mvx squared, delta t cancel, and the 2 cancels. Okay. So how about the total? So how about from all particles, not just from one particle, all particles on the wall? So what you need is you need to take the force from one plus the force from 2, right? And add up all of them. Now they move at different speeds, so they actually have different Vx. So I have different Vx for each particle. So when you take it, when you add these up, you need to sort of just do an average. I'll show you how you can do that. So you first plug this in, mvx1 squared over L plus mvx2 squared over L, right? So that's the speed of each of them. Now we'll assume it's just one gas, so all the mass is the same, or the mass of that particle is the same. So you add all these up. So you can pull out the mass per length. So you just have mx1 squared plus, sorry, vx2 squared, adding all these over here. And then you can now, here's the trick, you divide everything by n because you take an average. But you cannot just arbitrarily divide something by n. If you do that, you need to multiply it back by n, right? Now you didn't change anything, but now you've got a new concept over here. This is the average, sorry, the average velocities, because you're taking velocity squares, right? So put a bracket around this. Make sure your bar goes above the square, not below. So it's not the V average square, but it's V square, the average of V squares, okay? So this means average of V squares. This means the square of average V, okay? So be careful about that, okay? Times n. Okay, now remember that the kinetic energy is half mv squared, right? So the kinetic energy of, so an average kinetic energy is average of this, but the mass doesn't change, so you can pull out the m1/2 and m, so it's the average of v squares. We're very close to drawing together these two, right? But not quite, because this is v average, this is vx average. How does that relate? Well, v is vx squared plus vy squared plus vz squared square root, right? So v squared is that by Pythagoras theorem. Now, the average of them is just the same, right? But let's assume, so the average of things adding together, it's just vx squared plus vy squared average plus the vz squared average. Right? So the average grade of 3 people is just the average of each people's grade. That's what it's saying. So the average can be distributed into each component when you add them up. Now, let's assume the average x velocity is the same as average y velocity and the same as average z velocity, because it's random. So everything is the same. So that means this is just, everything is, if I make all of them equals to vx average, vx squared average, this equals to vx squared average. So this is 3 times, it's thrice of the vx squared average, okay? So in other words, the vx squared average is 1/3 of the v squared average times n. Let me put the n in front. Okay, now let's rewrite that into kinetic energy. Look at this and look at this. The trick is if I multiply top and bottom by 2, divide by L, you can see this is basically kinetic energy. Let me make it a little bit clearer. So let's say that's divided by, L. So I multiply top and bottom by 2, and you see this part is the kinetic energy. So it's 2/3 times n times the kinetic energy, the average kinetic energy of a single particle, divided by L. Okay. So what was the left again? That was the force of all particles on wall. Let's multiply the L on the other side. So force times L is 2, 3 n kinetic energy, the average kinetic energy of an individual particle, of an individual. And force times L, as we started off, was PV. This is the conclusion. So that's why without the derivation, it kind of doesn't tell you much. But notice this is linking the macroscopic, as promised, linking the macroscopic variables with this. So now what you can do with this is this. if the question tells you, let's say I have a box of gas and you measure the pressure is 1 atm, and you take the volume 1 by 1 by 1, let's say it's 1 meter cube. Now you can actually tell me, I also need to know how many number of particles in there, but you can weigh it and then find out, right? So if you weigh it and the mass of that gas is 1 kilograms and you know the molar mass of things, you can find out, you can derive, you know better chemistry than I do, you can find out how many number of particles are in there. And you can tell me what's the average kinetic energy of a single particle moving in that gas. Okay. There you go. That's takeaway number 1. Okay. And so recap, PV is 2/3. Now, N kinetic energy averaged is also total energy, right? The average total energy of the system. This is average individual. So N times the individual is total. Okay. So keep both of these in mind. And now also remember the ideal gas law that says PV equals to NKT. So this must mean we have our second takeaway is that NKT must equals to 2/3 NKE average, right? Combining this with this, the right-hand side of these two, the macroscopic and the microscopic version together. Let's see, what do we learn? We learn that the average kinetic energy is 3/2 kT of one particle. So now, if you stick this is takeaway number 2, is if you stick a thermometer, instead of doing the very cumbersome thing that I just did in measuring the pressure and the volume, you just measure and tell me it's 20 degrees Celsius. First of all, you need to convert that to Kelvin. Now, this is your exercise at home to tell me in joules what's the average kinetic energy of a particle at room temperature. Okay, of one particle. Okay. And finally, I can actually reverse this and write T is, there's one more part over here. You can write this as the average speed square, right? So let me extend my box as well. And there's a second part to your question is, if the mass is, if the particles are, let's say, oxygen particles. So find out what's the mass of an oxygen particle, O2 molecule, right? We're looking at that particle is the O2. So Google that and also find out, so that's part A is this. Part B, find out what's the average velocity squared is moving at. So take a square, after you find out this number, take a square root so you can find the square root of the average velocity. This is actually called root mean square. So it's called RMS. Take the square root of, because here you have squared things. So your units is a little bit awkward. It's meter per second all squared. So you want to take a square root to get a number that is meter per second, right? So this is a type of average. It's called root mean square. It means the square root of the mean of V square, right? Let's read that one more time. The square root of the mean of V square. If you look at the symbol, that's what it means. Root mean square. One more time, square root of the mean value, the average value of V squares. So make sure this bar goes above the squares. Okay. So yeah, you can find that out. And usually things are moving at roughly 100 meters per second, all the particles in air, okay? So see if you get a number somewhat close to that. You might, if you, this is a rough estimate. I didn't actually plug in numbers, but you can do that. And tell me on Piazza, what do you get? But it should be something between, you should get something between 100 to 400. I think those are reasonable numbers, okay? So roughly that, okay? And the last statement here is you can rearrange this formula to make T the subject, right? So isolating out T, you get 3 mv squared over 3k. Just rearrange, combine here and here, rearrange it to this. And now you see, or combine it with this side, then you can get it's 2 over 3k of the average kinetic energy of one particle. Okay. Now this is the modern definition of temperature. You see, remember from the first day we say temperature is the average kinetic energy. It's a measurement of average kinetic energy. If I don't have this factor, temperature is exactly average kinetic energy. So therefore, this is the modern definition or the microscopic definition of temperature. So we're going back full circles. So we are going back full circle now to conclude, to see that temperature is indeed a measure. That's why we didn't say temperature is the average kinetic energy, because it's not. There's a factor of 2/3 and then divide by K in front, but those are constants, right? So it's just scaled by amount, right? So anytime you're told the temperature, you actually directly know the kinetic energy, average kinetic energy. So if I'm standing in this room, right, of 20 degrees Celsius, I can just divide by that factor, right? Plug it in 3 seconds, I'll know the average kinetic energy of these particles. And then if I assume the kinetic energy is half mv squared, if I know the mass of these particles, so most of the gas around me is oxygen and nitrogen, made up of air mostly. So I divide by mass, I know the velocity these particles are moving around at in my room. So now this ties up and concludes we have a very complete microscopic picture of what temperature is. And we know exactly what heat and thermal energy is from a microscopic view and a macroscopic view. All right, good. Next time is the subject of thermodynamics. So we are going to take, now that we know how ideal gas behaves in microscopic and macroscopic, how do we make machines out of that? The next time the goal is taking heat energy and turn that into work done. Okay? All right, see you guys tomorrow. Have a nice day and take care.